So this is the 6th part of my world building guide series for creating an Earth-like fantasy world. I'll link the playlist down below, so if you're just jumping in, you can start at the very beginning. In the last part, we mapped out air circulation, low and high pressure zones, and wind currents. So at this point, we have everything we need to map out our temperature and precipitation. And then the only step left after that is climate zones, which sort of feels like it's all coming together, doesn't it? Now, I will add that this step in the process is adapted from a 5-part series from a post in the Cartographers Guild by Pixie. Oh, I don't have their full name, but it's from back in 2014, and it's based on climates applying GeoF's cookbook in detail. I'll have all of that linked below. But it used GeoF Eddie's climate cookbook, which will again be linked. And their process goes through a lot of the steps that we've already done, but in more or different detail. And mostly what that guide was just to come up with the actual climate zones, whereas we're going to use our maps for a lot more than just that, which is part of why we have a lot more detail here. So there will be a few things that I'm going to be adjusting from that process and also adapting it in order to match the maps that we have created. I also want to note that this version, this step, right, of the world building guide is going to be a little bit different than the previous steps. Instead of going through and drawing everything out on paper, which takes a very long time, about 12 hours to do all the filming and the drawing and the map making and all the prep, which requires basically me to set up my entire desk for that and leave it like that for the whole process, basically requiring me to do it all in one sitting. I am using Photoshop and my drawing tablet to do these maps instead, and I've taken screenshots at all the steps in the process, and as we go through this video, I'll sort of have the maps that we're referencing up here, and I can show very clearly the maps we're creating, the steps we're in, and then all the reference maps. I'd love to know what you think of this down below, of whether or not you end up liking this better or not liking it as much. I'm hoping that this is at least comparable, because this is going to take me way less time to do and is going to be something that I can actually pick up and work on in little spurts instead of having to wait for an entire weekend where my husband can watch the kids and I can do this. So if this works for everyone, I can put these out a lot faster. But if you still prefer the paper method, I did go ahead and use that when I was creating the paper version or the blog version of this guide. So the blog post for my website will be linked below, and for the most part, those are using paper up to the steps that I've already mapped out. In the future, those will all be in Photoshop if I keep doing it that way as well. Alright, so here you can see all the maps we made in the last part. We have our air circulation maps on the upper left, pressure maps in the middle top, and wind current maps in the upper right, and then our ocean circulation diagrams at the bottom. Now, you will notice that these wind current maps look a little bit different, and I redrew them in Photoshop so you can sort of see the difference between them on paper versus in Photoshop, and I had to tweak a few things. In my last video, I had to put a correction in there because I went a little bit dyslexic and wasn't paying attention, and I forgot to switch the direction of the wind currents in the different hemispheres. So I've gone through and made that adjustment, and you can see that it very, very minorly affected these maps. It honestly really didn't affect them much at all. I probably could have left it, but I went through and tweaked it, and here's the corrected map, and yes, let's get started. So, precipitation. And if you've looked at the Köppen climate classification system, it gets very specific in the requirements for each climate region. When it comes to precipitation, a lot of the requirements are along the lines of X inches of rain throughout the year, the driest months having Y% of the annual rainfall, etc., which is a very specific, detailed level of precision. And additionally, some of the climates talk about the number of months that meet certain requirements, etc., and we only are mapping this on a 2 times a year summer winter solstice time frame. This is a screenshot from Wikipedia of the Köppen climate classification website, and you could just sort of see some of the calculations, and I'm not really a math person. So there are 4 main factors that affect precipitation in the order of most impactful to least. We have pressure zones, which are the most impactful, and low pressure zones where air is rising will tend to be wet, and high pressure zones where the air is sinking will be dry. And then prevailing winds. Winds carry moisture and rain from oceans to land, so onshore winds that blow from the sea to land will bring more precipitation, particularly to the coasts, while areas with offshore winds will blow basically air from the land that is drier. And then the next one is ocean currents. Warm currents will bring more precipitation, while cold currents will bring less. These will obviously affect coastal regions the most. You will also see areas of significant ocean upwelling will tend towards less precipitation, and areas of significant downwelling will tend towards more precipitation. And then last is elevation. As air rises, it cools down and it precipitates. Air moving over higher elevations will lose its moisture more quickly. Tall mountain ranges will force most of the moisture to be dropped on the windward side of mountains, leaving a rain shadow on the leeward side. However, for the scale we're looking at, only extreme elevation is really going to impact our precipitation significantly, so you'll see that come in once we get to those maps. Here's just a fun little graphic of the mean monthly precipitation on Earth. So you can sort of see the different areas. The dark blue is more precipitation and white is the least precipitation. So I thought it was fun. All right, so mapping precipitation. And I'm gonna kind of be looking at my notes here, just if you haven't already noticed that I'm doing that. But you wanna make sure that you have all your other maps handy. And we're gonna mark precipitation levels on the two maps with our landforms and mountain ranges marked already, right? So as you see here. And like usual, you'll have one map marked summer solstice, and one map marked winter solstice. If you're doing the colored pencil method, you'll need 4 colors that are easy to mark over each other. I like to use no color for dry, yellow for low, lighter orange for moderate, red orange for wet, and dark red for very wet if you look at my blog. But here, I did this on Photoshop and I used white for dry, or no color, yellow for low, a light green for moderate, a mid green for wet, and a darker green for very wet. And when I do this process, I tend to layer them. So I'll start with areas that have no wetness and then start adding levels of precipitation to that so I can slowly increase the darkness of the color that I'm using for that layer. Now, as we go through this process for basically all of the maps here and the climate one, it's really easy to make mistakes, so don't be afraid to go back and fix things. Honestly, the first time you do this, you should probably be expecting to have to go back and correct things a few times, so just be mentally prepared for that. It can be a bit difficult. But if you end up having too many extremely dry or too many extremely wet areas, you can go back and take another pass and be less generous with your precipitation or more generous, and try to keep all the factors we sort of talked about in mind as you do this. And something else to note is that there are so many factors here that we haven't considered, so you do have some wiggle room. So first thing to map is baseline rain. And it's basically just going to be a low level of rain everywhere that there isn't a particular reason for there not to be. So the areas that will not get baseline rain are high pressure centers, extending some east and west, the leeward side of large mountains, coasts with offshore winds, and continental interiors. Since we are essentially coloring in everything but these areas, I find it easier to go around and circle them and then color in everywhere else. So that's what we're going to do here. So first, high pressure centers, extending some east or west. So here is the summer solstice map, high pressure, and all throughout this I'm going to be using the summer solstice maps, just so you're aware. But look at your corresponding pressure map and locate the areas of high pressure and circle those on your precipitation maps. So then next is the leeward side of large mountains, and these are essentially the ones we sort of already have drawn here, or you can look at your elevation map. And all mountains or large elevation changes will create some form of rain shadow, but on a global scale, again, we're only looking for these larger rain shadows. So look at your elevation map and corresponding air circulation maps, and there are a few factors to consider here. So the angle of the mountain range needs to actually block the air currents. It doesn't need to be perfectly perpendicular, but it needs to be slightly perpendicular, at least in order to block the air currents. If the air currents are running parallel or almost parallel to a mountain range, you're not really going to see much of a rain shadow. So focus on drawing circles for rain shadows on the leeward side of mountain ranges, where the air currents are blowing fairly perpendicular to the range. And you might have a very slim rain shadow from your orange elevations, or around 2,000 feet, a slightly larger one for the orange-red elevations, which are around 5,000 feet, and a decent sized rain shadow for red elevations, which is 10,000 and up feet. You'll also see some of this rain shadowing effect in high and large plateaus. The difference you'll see is that the rain will still sort of come up the edge of the plateau, so you're not going to see it at that distinction of where the plateau starts, it might be a little bit further out, and it's going to be fairly small. So go ahead and circle these areas. So next, coasts with offshore winds. These are winds blowing from land to sea, which will have already lost their moisture. And look at your air circulation maps and circle coastal areas where the wind is blowing from a continental interior. If you have an offshore wind, but it is an island, a thin strip of land, or something else where the wind would have blown over water recently, you won't see this effect. So you can sort of see here in my wind current map that there are definite areas that are gray, right, where the wind is coming, gray areas where the wind is blowing offshore from the continental interior, so you should be able to gauge that fairly easily with our maps. And then the last thing is continental interiors. And this is just due to their distance from the oceans. Continental interiors will tend to be drier. So you'll want to reference your elevation map slightly for this, but circle the interiors of large continents where there's no water nearby, and this can extend slightly further towards the inside of those mountain ranges. You might already have some type of rain shadow effect here, but that's okay. All right, so here's the two maps I've referenced, not counting the elevation one, because you can sort of get the idea of that. And all of my baseline areas circled in purple. So everywhere inside of these purple, I'm going to leave white with no color, and then everywhere else I'm going to color yellow as low precipitation. So here's all those baseline rain areas filled in. So moving on to low pressure zones. Low pressure zones are going to be one of the bigger sources of rain in your fantasy world. These will increase the precipitation of these zones by 1 to 2 precipitation levels. Look at your corresponding pressure maps and shade the areas of low pressure on your precipitation map with the next highest color of precipitation. And areas that are currently dry will get yellow, and areas already yellow will get light green. For areas of extreme low pressure, color these in by an additional step. So yellow areas will become light green and light green areas will become mid green. So the top map here is my baseline rain map overlaid with the pressure map. So you can sort of see it there. And then the bottom map has that precipitation based on these pressure zones filled in. And you can see how I filled it out. So next is onshore winds. And these winds blowing from the ocean to land will be carrying a lot of moisture, as we've already said. So you can look at your wind currents map to determine where you're going to have onshore winds. How far these winds carry moisture will depend on the inland geography. A low-lying plain will have rains dispersed more widely, whereas if there are hills or other high elevation features, they will only extend slightly into that feature. So increase the precipitation level of these areas by 1. So you can see here that I've taken that previous map and overlaid my wind currents map so that you can see where the onshore winds are. And then the bottom map has those areas with the additional precipitation from the onshore winds filled in. All right, next, the windward side of mountains. So we want to increase the precipitation level once on the windward side of mountains where the wind isn't coming from a dry continental interior. This will probably layer over some of your onshore wind areas, but that's good because you would see a lot of rain here. So reference your elevation maps and air circulation maps for this step. This area will be where the elevation is increasing from one of the lower elevations, the greens, into the oranges and reds. And you can see this map here where I've filled that all in. Next is warm coast currents. Look at your ocean circulation maps and locate the red or warm currents, and then look at your air circulation map to find the type of wind in these areas. This warming effect from these waters will increase the amount of rain on these coasts, and you'll want to increase the precipitation level by 1 along these coasts and increase the effect depending on the wind direction. If you have onshore winds, the effect will stretch a little further inland, and if you have parallel winds, it will be a thin strip or non-existent. Don't worry about coasts with offshore winds. And you'll see here the upper two maps are the ones that I'm referencing, wind currents and seasonal ocean circulation. And then at the bottom, I've marked the areas that will be affected by warm coast currents with purple, and then I'm going to increase the level of those areas. So you can see that done here. So here we have all of those warm coast current areas filled in, and then next is the polar front region. And in winter, the polar front, which is the subpolar low wind belt, will sometimes break, sending bursts of colder, rainy weather towards the lower latitudes. And if you have a larger continent spanning at least 30 to 60 degrees, you would increase the precipitation level by 1 on the western side of the continental interiors, where the latitudes are around 30 to 45 degrees. In this map, I don't really have anything in this range for winter in the southern hemisphere. Like you can see, there's no large continental masses between 30 and 60 degrees. That southmost continent is too far south for this to be relevant. But the northern continents all have a little bit of this effect, mainly just the left two, where they're fairly large. They span 30 to 60 degrees. So now that we have marked all of these areas, you can neaten your shading to round out some of the sides and make the different levels more distinct. And if you made a lot of mistakes, just start on a fresh map. It's fine. All right, so here are the 2 final precipitation maps filled in for our summer solstice and winter solstices in the northern hemispheres. And you can sort of see there's a pretty big there's a pretty big precipitation difference in almost all of these areas, which means there's going to be seasonal precipitation differences, which is fairly normal in a lot of the world. Let's move on to temperature. So when using these seasonal temperature maps for later determining the Köppen climate classifications, we're mostly concerned with the distinction of temperatures that they use to differentiate their climate regions. So that's what I made my scale out of here. So you can see this. We have extremely cold, very cold, cold, mild, warm, hot, and very hot, and I have the temperatures noted in both Celsius and Fahrenheit. So there are a lot of things that influence temperature, and we will focus on the following. Factors that increase temperature, which are warm ocean currents. So where there are warm currents along the ocean, these will extend warmth inland by a max of 5 degrees, less if the winds are blowing offshore. And then also equatorial latitudes. Our baseline temperatures will factor this in. Factors that decrease temperature are cold ocean currents. This is where there are cold currents along the coast, which extend the cold inland by max 5 degrees, less if offshore winds, and then higher precipitation. The higher in elevation, the colder it will get. Being further from equatorial latitudes, again, our baseline temperatures will already factor this in. And then the escaping of the polar front. Areas where the polar front will break and release cold, rainy weather south of the subpolar low belt will have slightly colder average temperatures. And then factors that moderate temperature. So this is mostly going to be our maritime effect, which is oceans that heat and cool more slowly. So the temperatures along the coast will tend to be more moderate. And then for factors that make temperature more extreme, we'll have the continental influence, which is due to land heating up faster and cooling faster than our oceans. So the temperature in continental interiors will be more extreme. So here are some graphics of annual average temperatures on Earth. The top one is just annual average temperature, not seasonal. And then the bottom map is the average seasonal temperature range, and you can sort of get an idea of the temperatures on the map and how much they differ throughout the year. So moving on to mapping temperatures. And if you are also using Photoshop, you could follow the steps outlined by Pixie in his forum post. And there will be a few differences to how we apply the temperatures, so I would compare his steps with mine as you go. And also, while I did this in paper in my blog, I'm myself doing it on Photoshop. I didn't go back and reference his forum post, so I'm not sure how similar the way I did it is to the way he did it, but you have options. And so to factor in the base temperatures, we will divide our globe into 11 sections. Using some maths, 180 degrees divided by 11 is roughly 16.3 degrees per section. So I've marked those on the side of this map here with little purple dashes. And we want to center the hottest part between the equator and the Tropic of Cancer or Capricorn, depending on the time of year. So we will want 2 maps, like usual, summer solstice and winter solstice in the northern hemisphere. And you can see here in this map, I have the summer solstice. But on the northern hemisphere winter map, you'll have horizontal lines across your globe at the latitudes 75, 58.5, 42, 25.5, 9.5, -7, -23.5, -40, -56, and -72. And you will label these bands starting at the North Pole and working south: extremely cold, very cold, cold, mild, warm, hot, very hot. And then on the other map, which is the one that you see here, it's going to be the reverse, so just starting from the other pole, and you'll label the bands, from the South Pole, work up. And I would also just keep the mountain ranges drawn in it makes it a little bit easier here. But essentially this is what your map should look like. You'll notice that on the warmer hemisphere, we don't get all the way back up to extremely cold, but that's intended. All right, so adjusting these bands. So to do these temperature adjustments by hand, we will essentially be moving the lines, dividing the different temperature bands based on the different influences. So some factors will be a half step towards another temperature, as Pixie called them, or a full step. And my blog does this by hand, so you can look at that for how I do it that way. But here, my example on the left is a sneak peek of the next 2 steps. And it sort of shows what it looks like when I move the circled areas in the top map a half step in the bottom map. And in my process here, I did each temperature color in a different layer. So my colder areas are below the hotter layers. And so if I want to bring a warm area a half step towards mild, I would erase half of the warmer areas. And if I want to make it warmer, I would expand where the warmer layer colors reach. And since we made our bands roughly 16 latitudinal degrees apart, these half steps would be the equivalent distance of about 8 latitudinal. Wow, 8 latitudinal degrees apart. And in addition to moving these dividers, sometimes we will remove or add some. For example, if a coast of hot, very hot, and hot bands has a half step cooling influence, we are going to lose that very hot band in between our hot bands. And the reverse is also true. If you have a large area of a warm band and in the middle you increase a step towards being warmer, then you're going to have to add a hot band in between them. Alright, so maritime influence. To determine the maritime influence, you will need to reference the corresponding wind currents map. This influence will extend from your coast further inland on coasts with onshore winds and less for coasts with offshore winds. Although no more than the equivalent distance of 10 degrees max is going to be affected, and this influence also cannot extend over mountains. So maritime influence makes temperatures more mild, which means they will go in the direction of warm and mild. To apply this in areas experiencing a maritime influence, you will redraw the boundary of your warm and mild bands half a step further out, and repeat this for subsequent bands. Leave the boundary between warm and mild alone. So essentially everything that's not warm and mild, if it's colder than mild, it'll move towards mild, and if it's warmer than warm, it'll move towards warm. So you will see the mild zone will extend half a band out, the distance of 8 latitudinal degrees, into cold. The cold zone will extend half a band into very cold, and the very cold band would extend half a band into extremely cold. The warm band will extend half a band into hot, hot will extend into very hot, and very hot will be made smaller or disappear if it's extended into on the other side due to maritime influence as well. So you can see here on this map, I have circled these areas and applied the effect already, so you can sort of see what that looks like. And next is the cold and warm currents. So our ocean currents map has cold and warm currents marked already on these, so the areas we'll be looking at for this step is going to be pretty directly referenceable for us. And you will also want to reference the appropriate wind currents map as well. So depending on the temperature of the currents, these will either increase or decrease the coastal temperatures. They will only influence more mild temperatures, so warm currents will increase the temperature of areas from extremely cold to warm, while cold currents will decrease the temperatures of areas from very hot to mild. And these influences will extend inland by a max of 5 degrees and less if there are offshore winds. So you can see my 2 reference maps up top here, and then my temperature map at the bottom, and I'm sort of writing the notes on the side of what I'm doing just so you can sort of get a little visual reference. But I went through and marked all of these areas to either move a little colder or move a little bit warmer based off the effects. Continental. So the interiors of continentals are going to be more extreme, as we talked about already, and this influences is pretty strong, so it's going to be a full step change. So anything that is cold or colder will move a full step colder. Anything warm or warmer will move a full step hotter. So this is basically the opposite of our maritime effect. So cold will become very cold will become extremely cold. Mild areas will be shrunk a little, let the cold and warm band cut into the mild zones some, but that part is very insignificant. And then the continental influence will be inland areas that are at least 10 degrees from the coasts. Although if there are mountain ranges between your continental interiors and the ocean, these influences could extend up to these ranges on the inside of them. And you'll see here all of these continental areas are circled, and I have made them a full step more extreme. Next is high rainfall. So humidity will make your temperatures less extreme and slightly warmer in certain cases. So this is because humidity will soak up heat but release it if the temperatures are cool enough. So this is another full step effect that will bring very hot bands closer to hot, and cold, very cold, and extremely cold temperatures closer to mild. So again, here's my reference precipitation map, and then my temperature map where I've sort of circled in these areas, and it ended up being a lot of the map. So what I sort of ended up doing was just scratching out the areas that weren't part of this higher humidity section. So I went through and made those updates. And then next is elevation. So you're going to want to reference your actual elevation map for this step. We've only marked very, very rough elevations on our normal map. That's not sufficient for this step. But according to OpenSummit, if it's not precipitating, the temperature decreases by about 5.4 degrees Fahrenheit for every 1,000 feet, or 9.8 degrees Celsius per 1,000 meters as you go up in elevation. So in our elevation map, we had ranges for sea level to 500 feet, 500 to 2,000 feet, 2 to 5,000 feet, 5 to 10,000 feet, and 10,000 feet and up. So you can either estimate where the elevation jumps would be as you go, which is easy enough to do in my opinion. It's not that critical at a global scale to get it exactly right? Because your regional maps are going to be a lot more detailed. Or you can follow my table to provide an easier estimation. So you'll have to provide some logic as you do this, as some of our jumps are large, so you'll have to sort of find the middle ground here. And you'll also want to add any temperature rings that you skip over. So as you can see here at the top, in my little table, I have the elevation on the left, and then on the right along the top is going to be your different temperatures. So you just kind of have to cross-reference them to figure out what the effect is going to be. All right, so here's the references at the top. So I have my elevation map and I have that table. And we're going to be looking at everything medium elevation and above, so orange, and red. And I would start with one mountain range or area of higher elevation at a time. Because you're going colder, it can be hard if you start at the lower levels and say you move it from very hot to hot, but then you can't distinguish what areas were hot before and need to go to warm and what you just made hot, right? That can get hard. So either start with the coldest areas and then do everything that's very cold, then do everything cold, then do everything mild, etc. And you can just do a single range at a time as well if that's easier. So you can see here on the bottom, I've sort of circled these areas in, and it's sort of hard to see at this scale, but I circled everything in orange that was an orange area. I circled everything that was red in a red area, and everything in that very dark red as the highest elevation color. And so I've sort of gone through and mapped that out to increase the temperatures. Last is the polar front region, and again, this doesn't really affect my map here for this solstice, but in the opposite one, it does affect the northern hemisphere. But in winter, the polar front, or subpolar low wind belt, will sometimes break, sending bursts of colder rainy weather towards the lower latitudes. If you have a large continent spanning at least 30 to 60 degrees, decrease the temperature by a half step on the western side of the continental interiors, where the latitudes are about 30 to 45 degrees. And again, this isn't relevant for my summer map, but you'll see the effect if you look closely on my winter one. So here are my two complete temperature maps. And you can sort of see that this all sort of makes a lot of sense. Having a really large continent in the winter hemispheres will mean that it's going to get a lot colder, mainly because of those continental influences. And when you have large continents around the equator and warmer hemispheres, that's going to be pretty warm. So I sort of have that sort of extreme effect, which you can see here pretty clearly, I think. So last step in this part is aridity. And it's a bit of a complication. And aridity isn't as simple as a lack of precipitation. Even if an area gets a moderate amount of rain, if it's so hot that all of that rain will evaporate or transpire, there's going to be a shortage of water. So I have a bunch of graphics here, but basically potential evapotranspiration, or PET, is the environmental demand for evapotranspiration, or the lack of, or the total water evaporation and transpiration if there's enough water available. The aridity index, AI, looks at the ratio of annual precipitation to PET, or potential evapotranspiration, in order to determine the dryness or water deficit in a region. And this index determines if an area is hyperarid, arid, semi-arid, or humid. With the Köppen climate classification system, the precipitation must be compared to a region's potential evapotranspiration in order to determine if a region is arid or semi-arid. This makes a lot of sense when you point out that warmer areas will have more evaporation than colder ones, and you will need to have more precipitation than evaporation to have surplus water. So ignore the fact that this graphic here on the bottom is in Dutch, I think. The images show the different ranges of precipitation to evaporation, so I believe the leftmost one on the bottom is arid, and you can sort of see that little blue mark is the precipitation, so a little bit of precipitation to a lot of evapotranspiration due to the heat. Then the next one is semi-arid, and you can see that there's slightly less evapotranspiration but still not a lot of water. The next one is semi-humid, and that's more water to a bit of evapotranspiration. And then the next one is humid, which is a lot of water to only a little bit of evapotranspiration. All right, so I don't like math. So in order to take this aridity into consideration, we are going to use a table that was shared in Pixie's forum that takes the PET and aridity index into effect to determine what precipitation and temperature combinations would produce arid, semi-arid, and humid climates, which I sort of made my own version of this table here on the top just to make this a little bit easier for me. And you can create another version of your map here for aridity. Summer solstice at the top of one, winter solstice at the top of the other, you know the drill. And typically modern scientists will only look at the warmest half of the year to determine this, so we only need to reference the summer half of each temperature map, and then both of our aridity, and then both of our precipitation maps. So you can see here on the bottom, I've sort of cut both of my temperature maps to just be the summer solstice and merge them together so that I can just more easily look at it. So for mapping aridity, I like to work with one precipitation level at a time and cross-reference each section with the summer temperature. And I took that table from before and sort of color-coded it to match the aridity that I'm looking for. So I'm just sort of going a little area at a time, mapping it out, because you're only selecting 3 options: arid, semi-arid, or humid, which makes it a little bit easier. But you can see my aridity map at the bottom for summer, and then here are my 2 complete aridity maps. And you can see, again, in the winter solstice on the northern hemisphere, it is pretty arid, which is not super surprising, but I thought that was interesting with how I selected my land masses. So a final map, final thoughts. We now have our seasonal temperature, precipitation, and aridity maps for our world, which allows us to get started on climate in the next step. And I've said this plenty of times, but I've done a ton of research here. Some of this information is pulled from various sources. Some of it is just sort of general knowledge in the fields, but in my blog I have linked a sort of just general reference page where I link a lot of references for different subjects where this information has pulled from. If it's a super direct reference, I do reference it directly, like how we've been talking about Pixie's forum post in here. But yes, they're all great articles and videos for further research as well if you are curious. But yeah, if you enjoyed this video, give it a share and let me know your thoughts in the comments on how you like this format. It's definitely very different, and I'm not sure if it's weird for you that I'm kind of looking at these maps as I sort of talk through it, but let me know below, because if this is great for everyone, I can make these videos a lot easier and faster. But yes, as always, if you have any questions, if you found any problems, which I have had people point problems out to me before, we've had to adjust some of these videos a little bit, or if you have a request for something that should be added to this world building guide, please feel free to contact me. But other than that, thank you for watching, and I will see you in the next one.